Along with t-test, we are going to take a quick, and I mean quick, look at Anova. And why are we going to look at Anova? Because t-test is sort of the foundation, sort of the ground. It allows us to look at one variable across two groups to see if the means are different. Anova expands that dramatically. It allows us to look at one variable or multiple variables across two groups or more than two groups. So the real power probably of Anova will be for us to be able to look at the variable in question across more than two groups. So first off, what is ANOVA? ANOVA is the analysis of variance. And it's an incredibly powerful tool and an incredibly complex tool, which is why I'm going to go over it in a very quick and simple way, because I think there's a lot of value and a lot of power in having the ability to compare two, three, four, five, however many groups, one variable across those groups. I think that would be very powerful to have from a data mining perspective. So analysis of variance is very much like t-test, as I've indicated, except for we can look at more than two groups. We can look at more than one variable across multiple groups. But in truth, if you are going to run a one-factor ANOVA using two groups, it's the same as the t-test. We're still comparing means across the groups of a particular variable or set of variables. We're still looking at the scatter of the data points around those means to see if there's statistically significant differences between the means. We're still also assuming that we have normal distribution and equal variances, and there are ways of running ANOVA if we don't have those. They give us not quite the same information, but it gives us useful information. We have an example in JASP that we can use, and it is the pain tolerance data set. So if you were to pull up JASP and want to take a look at this, you can look at you can select the pain tolerance data under ANOVA. So a little bit about this data set. We have four groups, and those four groups are separated by hair color. There are 19 subjects in our overall file. Three of them have 5 students, and one of them has 4. And what we want to know is there a statistically significant difference between any of the groups as far as pain tolerance? So we're going to run a one-factor ANOVA to find out. There are a couple of variables that we're going to have to take a look at. One of the variables we're going to look at is going to be pain tolerance. And the pain tolerance is what we call the dependent variable. The dependent variable is the thing that changes from subject to subject, and it can be impacted by any number of things. But it is the dependent variable. And then we're also going to be looking at another variable, and that's going to be hair color. And that's how we're going to group the subjects. So we'll group them by hair color, and we'll look at the pain tolerance within each of the groups and from group to group. That lets us sort of track the amount of variability that there is both within the groups. So if we're looking at the light blonde group, there's going to be variability in pain tolerance within that group. And there's also going to be variability across groups. So if we are looking at light blonde and light brunette, there's going to be a difference in the average variability across both of those groups. And that's another type of variability. The variability is important because that's a lot of what we track in ANOVA. We're calculating the means, we're comparing the means, but we're doing it in a way that takes a real close look at the amount of variability that we're able to track in our experiment. So, and here's what ANOVA will produce. So assume that we've gone through, and I'll do this as an example in JASP so that you'll be able to see this, but assume that we've gone through and we've done this experiment. And ANOVA has produced a table that gives us the following things. The first one is the sum of the squares. Now, that's not going to mean a whole lot, but I'll just go through it real quick. The sum of the squares is how much variability can we track within the dependent variable and across the variable groups. So that is a figure, a number that it gives us. And it actually will label it by the way that we grouped the subjects. So hair color, when we see the table, we'll see hair color, and it's telling us how much variability it's able to track from one hair color to another. That's going to give us information about whether or not those means are truly statistically significantly different. It also knows how much variability there is in the entire data set. And when we take that variability in the entire data set and we are able to deduct from that figure the amount that we're able to track that is varying from group to group, we are left with variability that isn't attributed to the different groups, and that's called residuals. So it's the leftover variability that we're seeing in the data that can't be attributed to the hair color differences. We also, in this particular case, do need to pay attention to the degrees of freedom. And this is weird because it's two different ways of calculating it. The first one, the degrees of freedom, is for the different groups, for the hair color groups. And we knew that we had 4 hair color groups. And what we do is we take the number of groups and we subtract 1. And that becomes our degrees of freedom for that particular known entity. Then we take the leftover variability and we calculate the degrees of freedom by taking the number of subjects and subtracting out the number of groups. There is a reason for doing that. It's buried in statistics somewhere, and I don't want to go into it. But it will give us our degrees of freedom for the residuals. This is all important because it's setting us up to get to a place where we will get to the truly important statistic, which is a little further down. Once we have the degrees of freedom for both the differences between the groups and the residuals, we can then calculate what we call mean square, and that's a simple division. That's taking the sum of the squares and dividing it by the degrees of freedom. We do that for the hair color groups, and we do that for the residuals. So that's how much variability can we attribute to each unit. Then we get finally to the most important thing, and that's the F statistic. The F statistic says how much better are we off when we compare the differences between the hair color groups than if we didn't do any of that work at all and we just took the straight mean. We derive that statistic by taking the dependent, well, what I'm calling the dependent, or really the hair color mean squares, and dividing it by the residual mean square. And that gives us our value for the F statistic. We want the F statistic to be fairly high because what that means is that it was able to track a good amount of variability for the differences between the hair color groups as opposed to what was left over. So it was able to track more variability going group to group, and that's a greater number than what we have that was left over. We also get a p-value for the F statistic, which is basically what's the chance that we derived that F statistic purely by chance. So the F statistic and p-value are the two most important because it tells us, first of all, is there a difference? The F statistic will tell you that. And can we believe that there's a difference? And the p-value will tell you that. The last thing that we get, and we actually have to turn an option on to get this, is the eta, or the eta squared. And that's the effect size. And what that tells us is how big is the impact of the differences between the hair color groups as opposed to the overall difference within the experiment. So we just basically take our hair color groups sum of the squares and we divide it by the total sum of the squares, the total variability, and that gives us the effect size. But like I said, the two most important are the F and the P. If you see an F statistic that is, on the order of 4 or 5 or 6 or some number higher than 1, then you're looking at some real tracked variability from group to group. And your p-value is it applies only to the F, and it tells you what level of confidence you can have in your F statistic. Here's how the Anova results are actually presented. So this is our dependent variable, the pain tolerance, a thing that changes from subject to subject. We group those into 4 groups called hair color. Okay. When we look at the differences from one group to another of these 4 hair color groups, we are able to see that we can track 1,360.726 units of variability by just looking from group to group. How much of the variability is actually tracked by just looking from group to group? We know we have 4 group colors, or 4 hair color groups, and so we take n-1 to get our degrees of freedom. Our mean square becomes the amount of sum of the squares allocated to each degree of freedom, which is basically simple division, and that winds up being 453.575. We do the same for residuals. Remember, we know we have a total amount of variability in this data set. We can attribute 1,360.726 units of it to the differences in hair color. What becomes residual is what we cannot attribute to the differences in hair color, and that's 1,001 units. Its degree of freedom is the number of subjects minus the number of groups. So that becomes 19 minus 4, which is 15. We take the sum of the squares, divide it by 15 degrees of freedom, and we get a mean square of 66.787. Now, here's what's really important. How do we get our F statistic? Our F statistic in this particular case is 6.791, telling me that we are able to track a good amount of variability in the changes from group to group. That tells me that those means are probably statistically significantly different. We get this value by dividing the hair color mean square by the residual mean square. And in other words, we're taking the amount of variability, which we've converted using degrees of freedom sum of squares, taking the amount of variability and saying, okay, we have 453.575. We're going to divide that out by the 66.787 because this is so much higher than the residual mean square. We're going to get a fairly good favorable F statistic. So that's how we get our F statistic. Our p-value is just how much confidence do we have in the F statistic. And then the effect size is anywhere from 0 to 1. It's basically what percentage is your sum of squares for your hair color, the differences between the groups. What percentage is that of the total variability that was found in the data set? And that is what we get. That's how we interpret Anova results. But the important thing to see is that we have a good, strong F statistic and a good p-value. This other stuff just gets us here. It gets us to F and P, well, except for the eta squared. But these numbers, and these numbers do tell us. I mean, we do see that over half the variability can be attributed to hair color differences, the differences between the groups. So it does give us some information, but really we're looking at the F and the P. So we'll take a quick look at this. I'm going to go ahead and bring this up in JASP. I think I already have it up in JASP. I'm going to close this out, though, and start over. I'm going to close that as well. And this is the data set. So I brought in the data set, and as I indicated, we have hair color. Those are our groups, and there are 4 groups. And then we have the dependent variable, which is the pain tolerance. And these are just labels to indicate which, who's who and what's what. So I'll pull it up in Anova. Go to classical, Anova, and we just have to move things around so that we can get the results we want. Remember, the dependent variable was pain tolerance. That's the thing that changes from subject to subject. And the way that we are dividing those out into groups is by hair color. Okay, so we have 4 groups. We have 19 measurements of pain tolerance that have been grouped into 4 different groups. Okay, it gives us an initial crack at this. We haven't even done our assumption check yet to know that we have equal variances, but it does give us an initial pass. And this is pretty much what I showed you in the slides. We've got our sum of squares. How much of variability can we attribute to the differences among the groups? And how much is left over when we are done with that? We've calculated our degrees of freedom, which leads us to calculating our mean square values. We can calculate our F statistic, which is basically the mean square of the group divided by the residual mean square. And that gives us our F statistic, and it gives us our p-value. This tells us we do have somewhere in the data set, we have differences. There are statistically significantly meaningful differences. We just don't know where they are yet. Well, we're going to take a look at a couple of things. We might want to look at this descriptive statistics. This could potentially point us where our differences are. We have a big difference between 51.2 and 37.4. An even bigger difference between 59.2 and 37.4. So it gives us an idea where to look, but we don't have any confirmation of that yet. We have standard deviations, and then of course we have the number of examples. Under model, this is the sum of the squares. This is the process that calculates all of this. We're not going to change any of that, so we're good there. We are going to go back up to the effect size. I told you how that's calculated. It's basically what percentage is this figure here of the entire total of these two. So that gives us an idea of the effect size. But we kind of got a little bit ahead of ourselves because we haven't done the assumption checks yet. So we're going to do the assumption checks, and this one really only checks for equality of variances. So, and what that basically means, are the variances in each of these groups pretty much equal, pretty close to equal? If there's one that is way off, then what will happen here is we have to abandon our assumption that they have equal variances, and this p-value will be lower than 0.05. But the p-value already is 0.692, so we know that we're pretty good. We're okay. We can keep these results and use these results. The only other thing I want to bring up, and there's a lot of stuff here, but I'm not going to talk about it. The only thing I want to bring up is the post hoc tests. Post hoc tests allow us to see if we can gather more information about the differences that led to this good F value. So the only way that we've grouped things is by hair color. So we'll go ahead and move that over to the right. And we're going to change, the default is the Tukey, but we're going to change to Bonferroni. It's one of the more common methods of doing a post hoc test. And what it does is it goes through and it takes each of the groups and compares it to every one of the other groups. We calculate the mean difference, we calculate the standard error, we calculate a t-statistic, but most importantly, using the Bonferroni method, what is the p-value? Okay, so we see that we have differences here, we have standard errors here, we have t-statistics here, but is any of it reliable to the point where we would want to pursue it? That's where this p-value comes in. So we can look at the first one, doesn't quite meet the 0.05 threshold, so we're not going to pursue that one. The next one is a terrible p-value, so we don't really believe that data at all. The next one's almost as bad. And then when we're comparing dark brunette to light blonde, those two groups have a significantly different comparison, significantly different means, and we can believe it. It's based on good value data. The data points have led us to a result that gives us a t-statistic, which is negative, but still that's typically taken as an absolute value. And it's very reliable. So this is one area where we can look for differences in the means. And then the next one, which just under the threshold, gives us the light blonde versus light brunette with a p-value of 0.049. So there's probably a statistically significant difference between the means of those two groups. That is pretty much Anova in a nutshell. I'm going to bring up another example. We'll pull up a new file, open this file, and it's going to be from the data library under Anova, and we're going to pull up Facebook friends. This is a review of some scores. It's an arbitrary score based on the number of friends that they have, a range of friends, and this is each of the participants. The only reason I'm bringing this up is because when we pop this into Anova, we're going to go back to classical Anova, our score is going to be our dependent variable, and the way that we group these is through friends, and it's going to do its best to give us a set of data, or set of information, some of the squares, degrees of freedom, the mean squares. The F statistic is 4.142 and the p-value is 0.003. The challenge with this data set is that we don't pass our assumption. We don't have homogeneity. We don't have equality of variances. Our p-value is lower than 0.05. So that basically means we got to abandon the assumption that we have equality of variances. And these results up here are probably not valid. They're probably not going to be useful, which is kind of a shame because there's good information up there. And if we could pass our assumption checks, we would be able to see that we do have differences amongst our groups. But we can't do that. We can't use this because we don't have equality of variance. So what we do instead is, I'm going to have to change the size of this, is we abandon what we call the parametric approach, which is what this is. This assumes equality of variances and that data would be distributed in a nice bell-shaped curve. We have to abandon that and come down here and go to what's called a non-parametric test. This is one that doesn't make those assumptions that we have equality of variance, and it doesn't make the assumption that we have evenly distributed data. So instead, we pop this over here, and it gives us this Kruskal-Wallis test, which tells us, okay, gives us a statistic. It's a fairly high statistic. We have a degrees of freedom of 4 and a p-value of 2. Seems to suggest in a non-parametric way that we do have some differences. But where are they? So what we'll do is we'll go back to our post hoc test. We will pop this over into one we're going to look at. We don't care about Tukey. We don't care about any of these. We care about done. Done is one we can use for a non-parametric test that will give us, okay, for our 4 groups, we're going to compare to all other groups, very similar to the way that we did it with the Bonferroni in the earlier example, but we'll compare to all the other groups, and see if we can find anything that's telling us that we have useful differences. We don't see a p-value here on this one, so that is a bit of a challenge, but we can still use some of the higher T statistics to say that maybe we want to look at a comparison of 302 to 902, those two groups, to see if there's a difference in those means. Then what we could do is we could just separate those two groups and run a t-test on that. We would also have to account for that. We would have to check to see if the assumptions worked out for a comparison of 302 to 902, because they may not. If they may not, then in our t-test, we would have to adjust for that. But it's a way of being able to sort of see when we don't pass the assumptions that we have another option. We can use the non-parametric test, and then we can use the done as the post hoc to see kind of group-to-group comparisons. For this week, I have created a file for you that is a list of 80 plants, and the plants are divided into 4 groups of 20 in each group. And what we're focusing in on here is how were those plants fertilized? They're tomato plants, by the way. How were the plants fertilized, and what is the average weight of the fruit that was derived from each of those plants? So we are going to see if there's a statistically significant difference in any one of the groups from any of the other groups, and if that leads us to a conclusion that, in fact, one fertilization method was better than another. So I will have you load the file. I'll put it into the module. I'll have you load the file up and drop it into JASP, and then bring it into Anova and do kind of the same things that I have done. I do believe it passes the assumptions checks, so you'll be able to use the standard Anova. And go ahead and take a look at the descriptives, verify that it passes the assumption checks, and then give us a post hoc test result. I would use Momferonia. It's probably the best one for this. Then to put all this into a Word document and include a paragraph that basically says what this means. Okay. Now in this particular case, we know what this means. We know that there's differences between certain groups, and we can actually track in the post hoc test which ones were significant. But with your tomato data, that'll all be different. So you'll have to take a look at that and get that done, and turn that in as your second part of this module's assignments. So you'll have the first part was for t-test, and the second part is for Anova. And if you have any questions, let your instructor know.